think we're recording now. Okay. Welcome, everyone. And welcome back to people who have been following. This is our 17th session. And also about 9 sessions ago, we started some coding exercises. So we have all of the recordings posted on Hackaday. This is the Quantum Computing Through Comics class. And all of the slides and past recordings are there. And you can jump around. You don't have to follow from the beginning in order, because we also have repeated content. Maybe it helps you if you say, looking at Groovers, we had a theoretical Groovers class, several sessions pass. There are several sessions in between them. You can skip. So all of the titles are there and the content are listed on the Hackaday's slides, so you can see what are the relevant materials you want to look at. If there's no special events like last week, we have a 30-minute to an hour discussion on one topic. And we use the Microsoft's Q# as well as the quantum katas for code. We've done quite a lot of classes so far already. And for people who have been following, I really would say congratulations to follow to this point, because we have already covered a lot of the basic concepts, linear algebra, and we did coding, and we talk about quite a few different types of algorithms. And for people who have seen like Grover's algorithm, Deutsch-Holzer algorithm, and some of the other algorithms that uses entanglement, like communication algorithms, and also interference, that you kind of have probably have a feel of how useful computing could be. And you can see the power of quantum computers when is using all of the basic concepts, superposition, entanglement, and interference, that we can really harness to make algorithms that's more efficient for certain tasks than classical computers. And it's also very nice that I've getting feedback from learners telling me where quantum computing clicked for them. Because at the very first time when you look at it, it might not be immediately obvious, but then after several classes, some people really understood, oh, this is how it works. And then it becomes, there's a learning curve, but then it becomes easier for them after that point. So thanks for the people who have been giving me feedback. So today we're going to talk about Shor's algorithm. That's one of the most famous algorithms, and that's also kind of, if you look at a lot of learning materials, is not taught early, because it really is using a lot of the concept that we learned before. So if you're following up to this point, pat yourself on the shoulder. You're really getting, is no longer really introductory anymore. You're looking at it that is using these concepts and can really show the power of quantum computing by using these special properties for quantum mechanics. And Shor's algorithm is also one of the useful algorithms, not just for academic training. It actually has an application that could be very, very impactful. Shor's, you can even find his own explanation of his algorithm. This algorithm is invented by Peter Shor in 1994. And there is a nice 2-minute video on YouTube, Peter Shor himself explaining it. So in fact, and now a minute and a half into the video, he's kind of summarized everything that we learned in the past. And then he just used a couple of sentences summarizing how really Shor's algorithm works, but he called it, I think he's being modest, he called it quantum algorithm in general, but it is really using interference and entanglement. So I recommend this video, very short, very succinct. But at the first time when you look at it, may not have seemed that he's really explained much. But then after you go through Shor's algorithm a couple times and go back to this video, you will see that's actually exactly what's happening. It's a great video. I don't know why people are downloading. There's always people giving. But let's just take a look. What's Shor's algorithm used for, and how does it work? We're going to spend a couple of classes discussing this, just like how we did with Groovers. I think for a lot of these algorithms, the very first time you see it, it might not be obvious. But after a couple of times, you see the pattern. So Shor's algorithm is used for, and also is a potential threat to the current RSA encryption scheme. This is of our encryption methods to encode messages. I'm not an expert in cryptography, and there are a lot of already existing write-ups and documentation about specifically how RSA works. So we're gonna do an overview just for the sake of the level of this class. We're doing, we would do a very short overview of this. And so how RSA works is it uses a public key and a private key for message exchange, and it's relying on some mathematical facts. So here Bob has a public key, and he uses this public key E to encrypt a message using this m to the power of E mod n, and n is a number. And turned out the number needs to be really, really large. We'll talk about it in a bit. So n is public, E is public. So he does this encryption and then sends the message to Alice. She then uses a private key to decode it. So C to the power of D mod n will give her the original message. But it really relies on the really large. So the few mathematical facts that RSA is using is basically these four equations. E to the power of E and mod n will give you the original message. So you can check the math, that's how it is. And n is a very large you can create by multiplying two also pretty big, could be big numbers, P and Q. And these two numbers are unknown. So if you know these, if you created this number n using these two numbers, you know what it is, and you will get, doing multiplication is very easy. But if you just know n, if it's really big, it's very difficult to factorize and get you these two numbers. And there's another number involved, R, that also relies on P and Q. And then you would need this E times D mod R equal to 1 to be your condition. So this is basically how this whole RSA is using for facts. And publicly known numbers are N and E, but the other four, P, Q, D, and R, are private. So if you want to decipher your message, you need to have the private key D, but you also have to know P and Q in order to get D and R. So if N is really, really large, is infeasible to factorize. Classically, we don't have any algorithm that is efficient enough factorization within a reasonable amount of time. Is not impossible, but it's just relying on the fact that we create a super huge N, and then relying on the fact that no classical algorithm can break that. And that's how we've been encrypting messages. So you can already sense the potential threat here. And especially with quantum computers coming in, there could be algorithms, as we will see. Shor's algorithm, very efficient way to break the factor of n. So let's look at a little bit more. So here's that we have p given it a number or q. These are not very big numbers because we're trying to use it as an example, but in real case, they will have a lot of digits. And in consequence, the large number n will have many, 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 many digits. And then if we have p and q, we'll get r. And then we need to create two numbers e and d that are relative primes to n, and for which e times d needs to be 1 mod r. So say if you have e is public, so you have e equal to 13, then you have d for 9477 in order to satisfy this. So this means mod is if you divide r by e times d, the remainder of that equals to 1. That's just e and d is this number. So say if you have a message, just call it 123. You can encrypt it by doing this mathematical calculation. What's the remainder of this division? If you want to divide m by m to the power of e, then you will get this number here. So if you then, this is encrypted message you send to Alice. And if Alice wants to decrypt it, she would do this cipher, which is this number. And you also want to know the remainder of the division dividing m by cipher to the power of d, and you get 123 back as the original message. So that's just a numeric example to show you how this works. So you can imagine if n is really big, then RSA can be secure. But then Shor comes along saying, if you have a quantum computer, then I can really break it very efficiently. And not surprisingly, as we have seen earlier, all these very useful quantum algorithms are using entanglement and interference. We are doing that with Shor's algorithm again. So this class, we look at this at a very high level, and in the next maybe 1 or 2 classes, we'll go into details. I'll just walk you through the setup here. Basically, what Shor's algorithm does is having these several steps. You have a bunch of qubits that you put in, and you make them into superposition. So this is pretty normal by now. If you have followed previous classes, we're always putting all of the qubits into superposition. And then you can entangle these input qubits and output qubits. So you entangle all of your qubits. You have all these interdependent qubits and with all of the possible states in superposition. And then the next step is having some periodic states being the overall system state in superposition. And because it's periodic, and turns out that the periodicity is the number r, then you can do a quantum Fourier transform to obtain the number r. So this is a very, very clever part, the quantum Fourier transform. So for people who have learned other types of Fourier transforms in other applications, this is exactly the same idea, is that if you have something in a periodic arrangement, but you don't know what the periodicity is, you can do a Fourier transform, you can obtain a new set of functions in order to give you the periodicity r. Now, this is how Shor's algorithm will look like. Again, not looking at details. This is one step zooming in. So it's got all these input qubits, like what we see in Deutsch-Hose algorithm, Groover's algorithm. You have a bunch of input qubits and a bunch of output qubits. And this is the oracle that you always need for this kind of interference algorithms. You want an oracle that takes both input and outputs. And we're talking about a lot of qubits here because n is large, and you need to have a number. How do you know how many qubits you will need? So basically, you're looking at the binary system. So 2 to the power of number of qubits needs to be larger than the number squared. And then how many output qubits do you need to put in? Our number of qubits, it needs to be larger than n minus 1. In the next class, I will show you some detailed example. Look at what happens in these boxes. You're putting all of these in. So this H gate is what's giving you the superposition of all the possible qubit states. And you feed everything. What happens is that you have all possible states. F of x is the you have the encoded x here. So you will have a function of f of x that equals to a to the power of x mod n. And a here is a guess. So in the factorization of n, you classically probably just have to guess 1 by 1 is 2 of prime number of n is 5, a prime number of n, you keep guessing. In Shor's algorithm, we also need to do some guesses, but it will speed up using the rest of the circuit. So you will have in this box an entanglement of all these f of x states with all the possible x. And then afterwards, after this box, there's something happening here. What you were left with is a periodic set of states. And f of x equals to f of x plus r. This means this is a periodic state. R is the periodicity. So x is here. Adding a periodicity or pitch of r, you get the same thing. Adding another r, you still get the same thing. This is what a periodic state looks like. So after this box, you get this periodic states remaining. Then you feed all of them into the second box here. This is the quantum Fourier transform. As I mentioned, it transforms the state or the superposition of all these periodic states into another superposition of states, but then is a function of periodicity. How do we think about this? And there are actually quite a few analogies we can make. But I got especially inspired by the 1 minute explanation from Shor that this box, you can think about it like so what is a grating? So I'm throwing kind of new words to people, but we have seen this before. Remember the double slit experiment we did quite a few classes ago when we were talking about measurements. We have these double slit experiment that directly shows you the effect of quantum interference. Remember that we had an electron beam, which is itself quantum mechanical, and then you're shooting that onto this screen that has 2 slits. If you block one of them, you get this distribution of electrons behind the screen, behind this one slit. But when you unblock this one, it's not as people classically thought that will show 2 peaks like this. What happens is interference happens, and then you get constructive interference even behind this blocked region. And then destructive interference contributes to these dips. And dips could even appear behind the slits where you would expect more electrons. This is a direct manifestation of quantum interference. And in the quantum Fourier transform, we are using this exact type of interference. Instead of having 2 slits, now we have a large number of slits. It could be infinite number of slits. And you have this basically the periodicity R. So this is like a grating. You're shooting electron beams again, but it can go through all of these slits, and they could be infinite. And you don't really know the grating's periodicity, but then you can observe the interference patterns afterwards. And this can be, I think by now, should be kind of a familiar phenomenon that you can think about water wave or sound waves. If you have a lot of them interfering, you will get this interference patterns, which are also periodic. You can observe this, and you know that the after the interference, these patterns will have a periodic pitch that is proportional to 1/r. So it is what this grating does is a Fourier transform. It transformed from this space into a reciprocal space. So if you measure, if this is what you can measure, you will know the is proportional to 1/r. So in this way, you can infer R. So that's what exactly the QFT, the quantum Fourier transform in Shor's algorithm does. And it's really super cool. It can be used in all kinds of situations when you want to find the phase and find the periodicity of your setup. So that's how this is done. You just pass through all of your qubits, and then it does this transform and gives you what you are looking for. And that is very efficient. You can do this if we had a working quantum computer that's capable of running Shor's algorithm, then we'll be able to factorize this large number n very, very fast. And then our RSA encryption will be broken. That's why we're looking at it, and that's because we encrypt things more securely, perhaps using quantum algorithms. That's a really quick, broad overview. And also, I'm going to recommend some other videos that are kind of at similar introductory level. There is one on, is also using drawings called the How Quantum Computers Break Encryption. So it's a pretty fun short video that shows you more details than what I just talked about today, but we're going to go into that later. There's another one by series by PBS, and it's also a very nice high-level description about Shor's algorithm and how the Fourier transform works, and how what they are using instead of using gratings is looking at the phase is kind of a clock that is pointing at different directions based on how many remainders you have. So because Shor's algorithm needs probably several iterations in one's understanding to get it. So if you want, before we talk about it next week, you should take a look at some of the existing materials. There are a lot of mathematical descriptions too. We're going to go into some of that next week, and a lot of maths. I'm trying to not bog down by the maths, but we're going to look at some maths next week. So yeah, today is a quick class. All of the recordings are on Hackaday project. This is a frequently asked question. All the recordings and slides are posted, and you can also find it on YouTube. I also want to get a sense here, because I have been getting a lot of questions from people who are interested in quantum, having a career in quantum. And I wonder if there's any interest that we can do a Q&A session in that I can answer questions that people have about getting a career, getting a job in quantum computing. So if you're interested, feel free to let me know and post questions in the chat if this is something interesting. Any question about today's class? Very high level, very quick. And I also wonder if is this okay? Todd likes the idea of the I've got quite a few requests about it. So David Ishu likes it, so we can do that, and we can have people unmute themselves. Thanks, Thomas. Submit. Video got lost on many occasions. Voice got lost. Uh-oh. Okay. I apologize. Maybe the microphone is not pointing in the right direction. I'll see what I can do. Okay. If there is no questions so far about Shor's algorithm. Okay. Khalidus asks, are there any encryption that is quantum hack proof? I don't know. I don't think so. So I don't know if Taro is here in the class because he's an expert in cryptography. And Todd asked perhaps a primer FAQ for common questions, then cover more specifics. So, okay, you mean also other types of questions about quantum other than career topics? Yeah, we can do that. Yeah, we can do a general Q&A, and if you have any questions, I'll answer to the best of my knowledge. Lattice-based encryptions are quantum proof. Are these implemented? So, I mean, if we're using quantum methods to do encryption, that would be quantum proof. I'm not aware if we have implemented them. Sumit says yes. So if you can post a link here for people to look at, that would be helpful. Any university certificate for quantum computing? Yes, there are. So you have to look at universities that offer quantum computing classes. Microsoft has done quite a few curricula. So University of Washington has a class, quantum class. And there are, you need to be enrolled in the school. We also have a few courses on Brilliant. So Brilliant is an online course platform. You can also pay to get the classes is self-paced. So you have a certificate from there. We have the MS Learn modules that we currently have 2 classes, but we're gonna add more. So that's once you take them, you're also qualified. I think I posted the link in earlier classes before about MS Learn modules. Thanks, Sumit, for posting the wiki page of lattice-based cryptography. Into that. Is there a crazy project when quantum computer is going to be available for public use? We're working hard for that. We are making quantum computers available through the cloud, and currently there are several different architectures. We have a hardware session. You can look at on Hackaday. And there's so many different architecture, and they're all in developing stage. So there's more to do with development and engineering before we can release it large scale for individuals. There are also a lot of applications in industry that we're already supporting. Yeah, but for Shor's algorithm and Groover's algorithm, we don't have any existing quantum computer that can run them yet. So number of qubits is one thing, but also you have to entangle them. You have those systems, and you have to have a architecture that can support your application. Is there a minimum number of qubits that's needed for running Shor's? I think I read recent thousands of them, but I think we need more. I think we actually made orders of magnitude more. So this is definitely an area that is in debate. So Sumi said 30 million. So yeah, that's the order of magnitude I have seen as well, but I've seen arguments for different types. So I think I'm gonna stop recording, and there are already people asking some career questions here. Let's do a dedicated session for that, and in a couple classes, and we can focus on that. Thanks.